I have the pleasure to introduce our first invited speaker. This is Dr. Veselin Stoyanov from TOME AI at GUSA. And I'm going briefly to present him. He is currently the head of AI at TOME, which develops practical applications for LLMs. Previously, he worked at the Facebook AI, where he led the development for standard LLM methods such as Roberta and Muti. Array and their application to improve online experiences, for example, reducing the hate speech and bullying posts. He holds a PhD from Cornell University and a postdoctoral degree from Johns Hopkins University. Veselin, the floor is yours.
Thank you, everyone. It's great to be here. And first, I want to thank Svetla and the organizing committee for inviting me here. It's really exciting for me to be back in the city I was born and grew up in, Sofia, and talk about professional stuff. And I really enjoyed this event, meeting all the people in computational linguistics in Bulgaria. So about me, thank you for the introduction, Svetla. Just to add a little bit more color. So currently I'm at the startup called TOME AI. I'll tell you about it in a second. I work on real-world applications of large language models. I'm also currently an adjunct professor in the Mohammed bin Zayed University of AI in the United Arab Emirates, where we have a lot of exciting projects on large language models, collaborating with an AI company there called G42, and also another company in the USA, Cerebras, that is building hardware for large language models. And prior to TOME, I spent almost 10 years at Facebook. I started on the search NLP team. Then I worked on machine translation, cross-lingual representation, pre-trained models, large language models. And as I was doing that, it was really exciting time in large language models. I was really in awe of the power of these models, and I really wanted to see them being used in the real world for tasks that they can bring value. So that's why I joined TOME. Yeah, I'm very passionate about solving real-world problems through AI. And yeah, I think we have these models, but we still quite haven't figured out how to use them effectively and make them really drivers of economical value. So about TOME, we started as a new AI native presentation format, sort of a replacement for PowerPoint, but we've changed directions a bit, and we're now building an AI assistant for sales. Mostly this change was driven by the fact of us realizing that large language models are actually much better at extracting and synthesizing data than actually generating stuff that is creative, because we still don't know how to use that for everyday work applications. Yeah, so we are building this assistant who is your second brain, trained to do the task and help this one particular persona in sales well. And we already can see that when we focus and target a single persona, we can do much better than the generic things that are out there. Well, today I want to talk to you about work that was mostly done at Facebook. It's about large language models for the real world. It had three parts originally. First, I'll talk a little bit about computational challenges with large language models and how we can use sparse LLMs to address those. I wanted to talk a bit about alignment and instruction fine-tuning, but I decided in the interest of time to skip that part. It's also a bit out of date today. And then challenges handling multiple languages, so cross-lingual models. So let's start with the first part. How do we tackle the computational challenges, and can we build more efficient large language models using sparse models and mixture of experts? why do we want to train sparse models? Well, so as we were getting into neural models, we learned a few things that were sort of counter to what we knew about machine learning. First, big models are more sample efficient. So if you have less training data, actually, you learn better with a larger model. Very counterintuitive to how we grew up in ML. Big models are actually more compute efficient in some cases. So we have these curves of what's the optimal model for each amount of computation that you may have. And sometimes a larger model is more computationally efficient. And we also know that there are some capabilities that only show up in larger models. So for example, few-shot and zero-shot learning only happens in larger language models. So if we train sparser models, they allow us to get the benefits of a larger model with higher parameter counts while using less computation. So at the time, and this work is now a couple of years old, so a lot has happened in a couple of years. At the time, this was the most comprehensive study of sparse models for zero and few-shot learning tasks. And we showed that a mixture of experts or sparse models can result in significant computational savings, even at very large scales. We showed some differences, however, how dense and sparse models scale. We trained a 1.1 trillion parameter model, which at the time was the larger model and which still is pretty large scale, even for today's standards. So I won't go into details of what mixture of experts are. The idea is essentially that we have some feed-forward layers in the network that are active. So we have multiple versions of a feed-forward layer, and only one of them would be active for a given token. In the interest of time, I'll skip all the details, but just want to say that we'll be following a pretty standard sparse mixture of experts setup. And we'll compare them to a model that's dense, in which we only have a single version of the feed-forward layer, and all the parameters are active. So as it was done at the time, it will be alternating dense and mixture of expert layers. Use top 2 expert selection, and we would use 512 experts in each expert layer. So we for these experiments, we followed what was the most successful models at the time, which was GPT-3. This was back at the time where they did publish the details of that model, so we knew how many layers and parameters each model had, and we tried to essentially match their setups with our dense models. And then we had our sparse models, which were trying to match the dense dimensions of the models. So essentially, if you look at the active parameters of our sparse models, they will try to be the same as the active parameters of the dense model. Some other details: trained for 300 billion tokens, context size of 2048. That was standard at the time, and we generally follow the GPT-3 setup. So here's the results, and you'll see here in the red is the dense model, and in the yellow is the sparse model. This is evaluated on perplexity, in domain and out of domain data. And for perplexity, lower is better. And you can see that the sparse model is indeed for the same amount of computation. So on the x-axis here, we have the amount of data flops that the model used to train. So you would see that for the same amount of computation, a sparse model was doing much better. Although if you look closely, you may see that out of domain, the gap starts to narrow a bit as the computation increases. Here's the results for evaluating on zero-shot tasks. So this was using 6 tasks that were the standard at the time. Again, we see the same thing that the sparse model does better, the same amount of computation, and quite sizably so. And we can look at it in another way. We can look at the speed up factor. So we want to know how much faster can a model train to the same level of performance. So we'll compare the sparse and the dense model. So let's say if the dense model achieves 90% on a task in 4 zeta flops and the sparse achieves it in 1 zeta flop, then we'll say that the speed up factor is 4. So we can plot the speed up factors now. You'll see that we almost always see speed ups with the sparse models. You see that there's difference on different tasks for which we evaluate. And you also, if you sort of squint a bit, you may see that at scale that the gap, the speed up decreases. So the conclusions of these studies was that sparse models outperform dense counterparts for the same computation, even at scale. And we studied it at up to 6.7 billion parameters dense and up to 1.1 trillion parameters sparse. But the gap does appear to be closing with model size and computational increase. And improvements seem to be better in domain versus out of domain. So as we were doing this work, some interesting personal learnings for me were, one, that scaling is difficult. A lot of things that work at small scale don't work in big scale, and that we still have not explored sufficiently sparse models. So here's one example of how this works practically. So you can see here on the left, like what our initial results look like. It seemed like we're very disappointed. Sparse models didn't do better when we were training at scale. But then we discovered the bug, we fixed it, and we had the chart on the right. So there was a lot of little setbacks in the project like this. And we still don't know a lot about how sparse models scale. There is an extra dimension of sparsity that's in addition to all the other things you need to study when you scale models. There's many unexplored hyperparameters. At the time, Chinchilla was coming out and it was showing us that everything we knew about scaling was wrong. And that even affected more sparse models because you have even more parameters. So if the models that we had at the time were undertrained, the dense models, then the sparse models are probably even more so. But since we actually have had a lot of really exciting developments with sparse models, so we had at least these 3 models, DBRX, Mixtral, and Grok, that are all sparse. They have some level of mixture of expert sparsity, and they do seem to be doing much better than their dense counterparts. And I think there's also a lot more work to be done in terms of the techniques that we use to build sparse models. We had a paper about how we can think of mixture of experts as essentially sparse feed-forward networks. And there's some, if you think of that problem that way, there's some corollaries that come out of it that allow you to do the mixture of experts models better. So there is a link there at a presentation that I gave on that. And I won't go into much more detail because I want to get to the second part, which was the cross-lingual models. So I'll pause here for a second. That's the part on sparse models. If anybody has question about that, happy to take it now.
The last slide, you mentioned sparsing based on sparsification of the matrices.
Yep.
So have you made a comparison and evaluation between the different approaches of sparsing? I mean, the mixture of experts versus the sparsification of matrices.
Yeah, that's a great question. So I can point you to our paper. So I think the interesting part was there was shown that you can think of a feed-forward layer as a sparse multiplication, as a sparse. You can think of it as a key-value pair and sort of sparse multiplication, picking up the highest scoring keys, essentially. So if you think of it that way, that's essentially what mixture of expert is, but it does it in a block way. So each key selects a whole matrix rather than one line in your matrix. If you think of it as a continuum, you can actually have blocks of different size and select them. And when you do that, you can get more efficient implementations of mixture of experts. Happy to talk to you more about that, maybe in the break. So cross-lingual models. So this part of the talk, first I want to start by mentioning BGGLU, which was a benchmark for language understanding in Bulgaria. And this work was done with collaboration with a bunch of Bulgarian researchers in NLP, all put together by Drago Radev, who was a very dear colleague and friend and a really big figure in computational linguistics in Bulgaria. He tragically passed away, but we really miss him. He was not just a really great researcher, but a great human being. So just want to take a second to thank Drago. So multilinguality and cross-linguality, why is it important? I think we heard earlier from Ms. Georgieva that translation in other languages are very important. In the European Union, as people who come from a small country with a small number of Bulgarian speakers, I think we can relate to feeling less important sometimes. So we want to build models that are working for everybody, no matter what language you speak. When I talk about I'll talk about cross-lingual models. So just to contrast to multilingual models. So multilingual models will refer to a model that can the same model can handle many different languages. So for example, we can have a multilingual BERT model that you can train for spam classification in English. You can train the same BERT model for spam classification in Arabic. Or you can train an LLM that can understand prompts and respond in many different languages. So it can respond in Bulgarian, in English. A cross-lingual model, in contrast, can transfer the learning from one language to another. So if I have a BERT model that I train to do spam classification in English, in the same model without additional training can do it in Arabic as well. Or I can have a LLM that I fine-tuned for instruction following in English and can also follow instructions in Arabic, or I can train it for understanding, for classification, or I can prompt it in English and ask it to respond in Bulgarian or translate English to Bulgarian. So cross-lingual models are crucial to building inclusive NLP tools because you don't want to train your tools for all the languages in which they'll be used. That's just trust me, I was doing that at Meta, and it's just not sustainable. There's just too many languages and too much work goes into training each language for each training the model for each language. So for our work that I'll present today, we train a multilingual generative pre-trained model, which we call XGLM. To provide LLMs for speakers of underrepresented languages. It showed impressive few-shot learning capabilities in medium and low resource languages, as well as strong cross-lingual transfer capabilities. So yeah, the key really is the data that we train it on. We trained again the same. So this was about the same time. GPT-3 was the standard bearer in large language models. So we trained the same size model as GPT-3. We used more vocabulary, more terms in our vocabulary. So we had models with 564 million, 1.79 billion, and 2.9 billion, and 7.5 billion parameters. We trained it on the CC100XL training data, which was mined from Common Crow, and it included 68 snapshots of Common Crow. So we trained it on 30 languages from 16 language families. We used temperature-based sampling to make sure that we represent sufficiently all the languages. So if you look at the chart here, this shows the distribution of the data that we trained on versus GPT-3, and you can see that we did have a lot more data from the smaller languages, from the tail languages. So one interesting wrinkle here is if you have a multilingual model and you want to test it in many languages, how do you prompt it? So for non-English language, you can have your text, let's say in Chinese, and you can directly apply an English prompt to that text and then try to resolve the task. You can use prompts that are manually written by native speakers of that language, or you can translate from English prompts and you can do the translation either manually or automatically. So again, this was maybe a little bit different because at the time we had prompts for different tasks that were handcrafted, and we would look at the probability of words. But all of that had to be somehow translated. So we trained these models and we measured their performance on XNLI, which is the cross-lingual natural language inference task. And here in this table, we'll see essentially how we prompt is in the different rows. So in the top row is we use the handwritten English prompts. On the one under it, we'll use Chinese prompts only, also handwritten, then Spanish and Hindi handwritten prompts. And then we'll use the handwritten multilingual prompts. The multilingual prompts machine translated and multilingual prompt hand translated. And by multilingual prompt, I mean we'll match the prompts to the language in which the task is to be performed. So surprisingly, we were expecting that the multilingual, either handwritten or hand translated prompts will be best, but that's not what happened. So the English handwritten prompts actually perform the best almost always. So simply using the English template performed the best across languages, and that was quite surprising. Actually, subsequent work have validated that, and I think it's something that we still need to understand better and see how we can correct in our models. You can see, for example, in Chinese, you do get almost 15% better handwritten English versus handwritten Chinese prompt. And in Hindi, something similar. We also tried these models for zero-shot machine translation. So this was using the Flores 101 data set, which was covering 14 languages of the ones that we had trained on. So we would do this essentially zero shot. We did use 32 examples, but those are sort of just examples of the task, so the model can understand that it's translating. Interestingly, so two things. First, if you compare our models to GPT-3, you'll see that we were doing quite a bit better across pretty much all languages. And that's reflective of the fact that we did have more tail languages in our training data. And then you can see that also our models are performing almost as well as supervised models. And if you look nowadays, I think that you see a lot less work on pure machine translation because these multilingual large language models are actually catching up to specific supervised translation models. So some key learnings. Multilingual generative pre-training significantly advances the LLM's few-shot learning performance for a broad range of medium and low resource languages. Improving the performance for medium and low resource languages is not only a modeling challenge, but also a challenge in data collection, fairness consideration. We need to figure out how to manage the mix of different languages that go into training the models. And there's still interesting work to be done in multilingual instruction fine-tuning. And what's interesting that if you look today at the top proprietary language models, they're actually a pretty good multilingualist. So I can go and ask GPT-3, откъде извира Дунава? Where does the Danube River spring for? And I'll get a really good answer, actually. I can actually say, where does it, откъде извира Дунава, then translate and answer in English. And the model actually does that. It translated my question and it answered it in English as well. So it's also cross-lingual. And this maybe begs the question, why are LLMs natively multilingual? So here in this last part, I want to talk about something that a piece of research that I found very surprising and very interesting, and gives a kind of an interesting food for thought. So for a while, we have this hypothesis, and this comes from the world of word embeddings, that embedding spaces actually have very similar shapes. So if you embed word embeddings in English and embed word embeddings in Bulgarian, the embedding spaces will be similar shaped. So if you find a way to align them by using some common words, then all the words align and the two embedding spaces are aligned. So words with similar meaning have, are very close to each other in this embedding space. So this was even the first word embedding ideas, where if you took king and subtracted men and added women, you end up near the embedding for queen, and then that holds across languages. So the hypothesis is that when we train these multilingual models, because there's some code switching and other words that are in common between the texts of different languages, the embedding spaces of these large language models align, and then we get multilinguality. So we actually wanted to test this hypothesis, and we said, okay, well, what if we had some extra anchor points? So if we take some words, for example, we take something like, I went to the beach, and we replace beach with the Italian words spiaggia, then we'll be introducing an artificial anchor point. So our hypothesis is to introduce a lot of these new anchor points, the embeddings will be more aligned. So to test this, we trained BERT models. We added this extra anchor points to a multilingual BERT model. And now we can compare. So the dark blue bars are the original model, and the dark green bars are ones with the extra anchor points. So we'll see for English to Chinese and English to Russian, we have small improvements, but definitely not as big as we were expecting to see. So we said, okay, what if we go the other way and remove all the anchor points? So how we can do that? We can essentially take our English text and tokenize it with one tokenizer, and tokenize our Russian text with a different tokenizer. So even if it's the same token, we give it a different ID. So there's no common tokens between the English and the Russian at all. And then we train a model. And the results we get are the one with the light green here, which are worse than the original model, but actually not that much different, only a couple of points. So what is going on? So we had to actually revise our hypothesis and hypothesize that the internal model spaces have the same shapes, but these spaces are not aligning because of the anchor points, but they're aligning because there's something in the representation. Maybe they're saving parameters that makes it more efficient to represent the same concepts close to each other. So how can we test this hypothesis? Well, let's do now another experiment. So instead of removing anchor points, we'll be removing parameter sharing. So we would take our standard BERT model there on the left, and we'll start splitting off layers. So we would say the first layer, we'll use 2 copies of it, and the 2 won't be shared, but they won't fit in the same second layer. And then we'll split the second layer and so on. So the more layers we split, the less sharing there is between the 2 models. And then we'll see what happens to the cross-lingual performance. So this was done in a 8 layers BERT model. And you can see if we split, so I think first we just split the embeddings in the dark orange, we lose a bit of alignment. Then we split the first 3 layers and we lose some more. And then if we split the first 6 layers, so we only have 2 shared layers and 6 separate layers, in that case, we get the performance that's pretty much random for tasks for Russian and Chinese. So that seems to validate our hypothesis that because they're trained in the same model and shared parameters, that actually leads to the alignment of the spaces. And compare this to anchor points, where removing all the anchor points only leads to a couple of points of degradation. I think that makes a pretty strong argument. You can also see that the word embeddings that the model learns are as good as what we used to do to artificially align embeddings, word embeddings with fast text. So I won't go into much detail, but if you just get the embedding, take the embedding tables out of BERT, it's already pretty well aligned multilingual embeddings without having to do any additional alignment. And we can run another experiment. So here we compare a monolingual model in which each model was trained separately on the same training data, to a bilingual model where one model was trained on a joint training data. And again, we'll remove all anchor points. We actually can train 2 English models. So you can think of, we have subdivided our English corpus into 2, and we have tokenized it with 2 different tokenizers. So there's no overlap between the tokens. They look like 2 completely different versions of English. And you can see that if we compare the bilingual and monolingual, so what we compare here is essentially we take a sentence, you compute its internal representations, and we look for the similarity of an English sentence and its equivalent, let's say, in French. So we use parallel data for that. And we see that when we train models jointly in the same model, the bilingual models have much better internal similarity. And we can compare those to a random model in which we use random weights. So there's still some similarity due to some interesting properties of these models. So I think, again, for me, this was a very interesting finding and sort of mind-boggling finding, that because essentially when you think of it, we take 2 set languages in or text in 2 completely separate languages. We don't know anything about them. We don't have any grounding. And yet when we train the same model, it aligns them together, which means that if you think of it, if today we found some lost language from a long time ago that we don't know how to speak, and we have billions of tokens of it. We can fit it together in our LLM with English, and somehow we will learn to speak that language. So some of the conclusions from this is that we don't need parallel or code switching data to train good multilingual models. We can use LLMs to do transfer from high resource to low resource languages. As long as we have enough data in the low resource language to learn this internal representation space, the high resource language can actually help. And also that means that maybe as the model size increases, we have to worry less about including a lot of data from low resource languages. But still we need to have at least enough text from the low resource languages to build good internal representations. So I think there's also some interesting scientific applications that, this argument, is there any universality of language? So maybe there is universalities, but maybe they're learned rather than, being native. And I think one other question that for me is very interesting is whether there'll be universalities across domains as well. So if we learn representations of images, would they be the same representations as the representations that we learn from text internally? And could we sort of align text and image without necessarily needing to do grounding? So interesting to see whether we can do any cross-model transfer the same way we do cross-lingual transfer. So yeah, my research interest making LLMs practical nowadays. I work a lot on the flip side of large language models, which is how can we make them work for everyday work applications, and sort of the engineering challenges around that, as well as the applied research challenges around building really high quality models, being able to work around some of the model's deficiencies, such as, not always being truthful to their inputs and so on. But I'm still interested in sparse LLMs, in multilingual LLMs, as well as instruction fine-tuning. Yeah, I think that's all. I wanted to have some time for questions in the end. So thank you all for your attention. I'm happy to hear questions.